All right, so I'm going to be walking through how to solve a one-way ANOVA by hand. And today we've got an explosive problem set. What we have here is the Manhattan Project was them working on the atomic bomb. It was out in Los Alamos. If you've seen Oppenheimer, you understand what the Manhattan Project was. So there were groups of scientists obviously working on this, and in this problem we have 3 teams of scientists. We have a theoretical team, an engineering team, and a math modeling team. And we're dividing them up to work on nuclear fission calculations. Nuclear fission is how they were able to achieve the atomic bomb. And so we got a sample of 12 here, 12 scientists in 3 groups, 4 in each group. And we want to see their problem-solving accuracy related to nuclear fission calculations. And we are looking at their accuracy scores out of 100. So kind of like a test, from 0 to 100. We're kind of looking at their accuracy. I've already written out some of the important things that you're going to first need, but I'm going to start with the first team over here and write out what this means and explain it. So the first thing that you want to do is you want to add up the scores. So this is the sum of scores. So you're going to add up 82, 79, 85, and 80. And when you add that up, the sum of scores, which is that EX notation, when you add those scores up, it equals to 326. Now, you're going to want to square each of these scores. So when you square 82, for instance, that's going to be 6,724, for instance, right? And you're going to do that for each one, and then you're going to add that up, which is the sum of scores squared. So when you add up after you square all of those, this theoretical group should equal 26,590. So now we can see that we've already done that for these other groups. So this is the sum of the scores. Then we squared each one to get this, and we did it here. Then you want to make a totals column. Your totals column is going to be, you're summing this row. So this means the sum of scores total. So you're taking, the total, overall total score of each team, adding it together, and that gets you 1,064. So you're just adding 326, 357, 381. That equals this number. Then you're going to do the same thing and get a much larger number when you add together each of these in this row. So the sum of scores squared. And so that's what this is. The sum of square, the score squared total, that's the T's for, is 94,766. And just for, to make sure you understand the difference, little n is 4 because each team has 4 scientists in it, or 4 scores from those scientists. And the big N represents that there are 12 scientists that have 12 different scores from their calculations, so from the tests that they were given to see their accuracy. So 4 per group and 12 total. One of the things you may be asked on tests by your professor is to name what the null hypothesis and what the alternative hypothesis is. The null is always going to say there's no difference. So there's, in the case of ANOVA, it means there's no variance. There's no difference between these groups. So if we're looking at like solving or doing part A maybe of a problem, it may ask to put the null and alternative hypothesis, which would be H0, that's the null, which means variance between these groups is equal to 0, meaning they don't vary. There's no variation between these teams and how accurate they are in solving nuclear fission problems. Then you get H1, which is your alternative hypothesis. And in this case, it's saying it's not equal to 0. The variation does not equal 0. So it's saying there is variation. This one is saying all of these teams are not going to vary. H1 says, these teams variation does not equal 0, meaning there's a difference between these groups and their accuracy of calculating nuclear fission. The next thing we want to do is we're going to take the sum of each group, so these, square it and put it over the number in each group. So we have to kind of go through these steps to get our pieces to plug in to our F table, which is what you ultimately use to solve a one-way ANOVA. So now in part B, I'm going to show you kind of the steps that we now need to take. So we need to find this value, which is the sum so this is the sum of scores of the group scores squared over n. All this simply means right here is that we're taking all this means is we're taking 326, which is right here. K is group, so we're taking the sum of scores group, first group, 326. We're going to put parentheses around this because we are going to square that number. And then on bottom we put n, which remember little n is 4 because we have 4 in each group, 4 scientists. And we're going to do that with each group. So then you're going to add 357, which is here. That's the sum of scores for this group. Squaring that, putting that over 4. And then you're going to do the same thing with the final group, 381. Squared over 4, like so. This, once you calculate it out, is going to lead you to 94,721.6. And so after that, we now are going to find this component needed to fill out our table, which would be the sum of scores total, which is this number up here, squared over big N, which is 12, right? So then you're taking 1,064 over 12. But you are squaring this. So you're taking this. This is why I have had this here. So 1,064. This is going to equal 94,341.3. Now you're going to take these numbers to find what's called your sum of squares between groups. So you're gonna want to find the S. Oh, I was trying to write the sum SSBG, and that is equal to this number minus this number. So it's equal to the sum of the sum of squared scores over the number of people in that group is equal to that value minus this value. So all this is saying is we're taking this value that we just calculated and this value that we calculated, and we're subtracting them. So 94,721.6 minus 94,341. What does that equal? It equals 380.3 is the SSBG. So the SS between groups, sum of squares between groups. Now, you want to find the total, the SS total, sum of squares total. So find SS total next. And so then that's going to be the sum of x squared t, which is this value, 94,766. And then you're going to subtract that from, this number, which is the sum of xt over n. So what you're then now doing is you're taking this number, which we know to be 94,000, 94,000, 94, so we're taking this number, which is 94,766, because again, this is the sum of scores squared total, which is right here. And then we're subtracting it from this, from where we got on this part, which was this value. So then we're doing 94,341.3. And that is going to equal our sum of squares total, which is going to be 424.7 is our sum of squares total. Now we want to find our error. So you have to have your sum of squares between group, your sum of squares total, and your sum of squares error in order to find to test the significance. So now you're going to find the SS error, and that is going to be simply is equal to SST minus I believe SSBG. So it's it's called sum of squares total minus the sum of squares between groups. So then you're going to subtract what you found here. So sum of squares total 424.7 minus 380.3 is then equal to 44.4 for sum of squares error. So now we have every component that we need. We calculated the sum of squares between groups, we calculated the sum of squares total, and we calculated the sum of squares error. Why do we need all of this? We need it for our table. It's called our F table. So we then have our source of variation, so if we make this table, we have source, and we have between groups, within groups, which is error, and then we have total. These are our sources of variation, and then we're going to put SS here. And so we got, for between groups, we got 380.3, so we're going to put 380.3. And for within, that's the error, that's here, we put 44.4. Total, that's SS total, which is here, you got 424.7. Now we've got the degrees of freedom, or between groups, we have 2, 9, and 11. And so you're going to take the between, and you're going to divide it by its subsequent degrees of freedom. You're going to do the same for within, and you're going to do the same for total. So remember, total degrees of freedom is literally just n minus 1 So 12 minus 1 is equal to 11, right? So you got 11. And between groups, degrees of freedom, is the number of groups minus 1. So 3 minus 1 is equal to what? 2. Boom. And what's left over then? 9 is left over, because they should add up. So these should add up to total. So 9, 10, 11. That's how you know you have the right number for the degrees of freedom, if these two numbers add together. All right, so now you're going to divide 380.3 divided by 2 to get your mean square, which is going to be 190.15. Then you're going to do 44.4 divided by 9, and that's going to be 0.93. Then you're going to take 190.15 and divide it by, this is a very bad 9, 4.93 to get your F statistic. So 190.15 divided by 4.93, that's going to get you an F of 3.57. I don't even have to look at the at the distribution of the table, the F table, because this is a very high number. So we can assume that this is significant even without looking at the critical values. So the critical value, though, if you did look it up on the table, would be plus or minus 4.26. And so it exceeds that. So we can now reject the null hypothesis that there's no variation, that all the groups are the same and how they scored on these nuclear fission calculations. And so how you write this up would be you go F, and then you're going to do your degrees of freedom for between groups 2. So this is like if you're doing a scientific write-up, and then 9, which is your within or your error. So you're going to do between groups, and then you're going to do your DF error or within, like this, and you're going to say it equals 38.57, and then you can say then comma P is then you say less than 0.05. Sorry, so my camera cut out there for a moment. This eta squared here that you can put in, it's you take the sum of squares between groups and you put it over the sum of squares total to get 0.89. And this is essentially a proportion. This basically means 89%. Well, what does 89% mean? It means that the variance in scores between these scientists, 89% of that variance is accounted for by the group that they're in. So we can say that the reason why their scores differ is that 89% of that difference is due to the type of scientist they are. A theoretical physicist, an engineer, or somebody that does math modeling. So that's what eta squared is. If your professor asks for that, it's like a percentage. So 89% of the difference that we see between groups is accounted for by the type of scientists they are, or simply which team they're in.